I'm ready. All right, good afternoon. We just finished the topic of short channel effect. And instead of short channel or so narrow width, reverse short channel, reverse short width effect is what we talked about. Just to highlight one thing about short channel effect, I want to point out that it's desirable to have a small XD max, small depletion layer under the channel. It's desirable for short channel effect, right? One way to understand that is that that's the dielectric thickness of the back gate. If the front gate should be thin, well, back gate should be thin also, right? That's quite reasonable if you look at this electrostatic problem. So how can we make the X depletion small? You can do this by using heavy doping. When you do that, however, you're going to find the VT may be too high, higher than you need. All right? And it can be shown, I think we might have done some of that, maybe not. If not, this could be a good homework problem. It can be shown that with this type of a step retrograde doping, that NEC group called the delta doping. What they mean is that they just use ion implantation to create a very heavily doped P plus layer below the surface. And this is done with a very special technique, and you should read the reference in the handout volume 2, and you will see how that's done. It's not just straightforward implantation, it's actually implantation plus a low temperature epitaxial growth, so that they get a very sharp transition from P plus to P, and then they can keep the lightly doped P region very shallow, very thin. All right? By doing this way, if you have such a step function doping transition from P plus to P minus, you can show that you can reduce this depletion region thickness by a factor of 2 while maintaining a given desired threshold voltage. All right? Does this sound totally new to you, or we have talk about it a little bit? Anyone can help me? Sure? Okay, that's fine. Take my word for it. You can take this as a exercise for the reader. Can you find a? In fact, I just remember now we did do that. I did do that in the lecture. I remember with you. All right. So so that is the attractiveness of retrograde doping. It really is that. All right. Not many people realize that's what it is, and certainly. People don't put it in those terms, but that's really what it is. It allows you to reduce the depletion thickness by half while maintaining a desired VT. Therefore, it's desirable. Now, what's special about this delta doping idea is that not only they make this transition very sharp, they also make the P plus region very thin in such a way that by the time you reach the depths of the bottom of the M plus source and drain junction, the boron doping concentration is no longer very large. Now, what's the benefit of that? What's the benefit of that? In other words, what's the benefit of keeping this M plus so thin such that it terminates before the M plus junction edge compared to a case where you just make this whole thing P plus? Right? What's that? Sure? All right. Okay, sure said. Next time speak in the microphone, please. He said that this reduces the junction capacitance. That is correct. All right. So one disadvantage of retrograde doping is that you're going to have a P plus here to give you M plus P plus junction. Junction capacitance is larger. So if you can do this, then you can reduce that. Okay? This is a research paper, but just give you some idea what can be done. Once you know what's desirable, then you can invent interesting technologies to do interesting things. All right. Now today we're going to start a new topic that is a more accurate IV model. And there are several things we can talk under this umbrella, I suppose, but we're going to particularly look at two things under the section 5.4. I probably mentioned this before, that if this short channel effect is one core theme of this course, then this will be the other core theme. There are two core themes. That is, what controls the current? What determines the transistor current? And maybe I should add, what controls transistor current beyond what's covered in the first order IV model that we have already reviewed in chapter 4. And that's the second important core of this course, and this is where we are right now in this section 5.4. All right, so it's an important section. But turns out there are two important improvements over the first order model that we have known about IV characteristics of MOS transistor. One is that mobility is a complex function. It's a function of the vertical field, but actually, if we really talk about it, it turns out it's a function of EG, it's function of TOX, it's function of doping concentration, it's function of substrate bias. At least these things can influence the mobility. Now, maybe I have omitted one thing or another, maybe not, but at least these four things are known to have significant impact on mobility. We're not talking about 10% mobility change. We're talking about a factor of 2 or 3, right, compared to what we can get in a bulk example. So these are important. And later what we'll see, interesting concept is that they all have to do with the vertical field. So as the vertical field gets stronger, mobility decreases. And we'll look at that. And first, what it's about. And secondly, how do we include this mathematically into the IV model? All right? We'll be doing that. In a similar fashion, we're going to first talk about, well, we'll talk about how to include velocity saturation phenomena into the IV model. And this term is not new to you, I believe. You have all heard this one time or another, something called velocity saturation. That is, the mobility is a function of the horizontal field, or mobility is not constant. As we increase the electric field between source and drain, mobility drops, all right, in such a way that eventually velocity remains constant, does not increase with the increasing electric field anymore. And this is known as velocity saturation. All right? So we're going to work these two things into a refined IV model that's going to give us several 100% different result compared to the basic IV model. All right? Okay? All right. So 5.4.1, we first look at the mobility dependence on the vertical field. And perhaps you can also call this transverse field. Vertical meaning we usually draw the transistor in this manner. So the direction this thick arrow is pointing is called a vertical direction. And that's the field we're talking about, all right? As that field increases, mobility decreases. I guess perhaps a little bit more, more geometry independent, or at least drawing independent word would be transverse field, meaning the field that's normal to the direction of the motion. The electrons is moving from source and drain, right, under the influence of the horizontal field or the longitudinal field. But turns out the mobility is function of the transverse field or the vertical field. All right? So that's what we're going to be talking about today. All right? Okay. First, how do we measure mobility? What do we do? Well, what we do is to measure mobility, we use this equation. We use the equation that ID is equal to W times mu. Can we zoom in a little bit more on this lower right corner? So look at this equation. ID is equal to W times mu, thank you, times Cox divided by L, Vg minus Vt times Vd. You recall this equation, right? All right. This equation is only correct under one assumption. You probably remember what that assumption is. That is small Vd. Otherwise, there's a minus Vd over 2 or m times Vd over 2 term here, right? So this is good for small Vd. For example, when Vd is equal to 50 millivolt, right? That's fine, because we're going to make the measurement, so we can always choose small Vd when we make this measurement. So if we choose small VD when we make the measurements, we can use this equation. Now if you look at this equation, ID can be measured with a current meter. W and L are supposed to be known. Mobility, yes, unknown. Cox supposed to be known, right? We can measure it from CV measurement or whatever, right? VG is known. You measure it. I mean, you apply this VG. VT can be measured. We looked at how to measure VT before. And VD is what you apply. So the only unknown on the right-hand side is mobility, right? So therefore, you should be able to measure mobility. And indeed, this is the basic method to measure mobility, all right? There's no other method that's convenient to use other than this method. So you do see all the data reported using this method. When you actually make the measurement, however, you will find the equation, the result looks a little perhaps surprising. According to this equation, ID should be a linear function of VG. ID should be a linear function of VG. If we plot ID versus VG, should be a straight line. In reality, if you plot ID versus VG, this is what you'll see. It's not straight at all, right? In fact, I think I probably stretched this a little bit even to show you a portion that seems to be straight so that you can draw a curve, extrapolate a straight line from that straight region and get VT. In reality, there's no point in here that's straight. Okay, this whole curve just a rounded curve. That's what you'll see. And the only possible explanation, and which is correct explanation, is that mobility is not constant. Mobility is a function of VG. Okay? All right? Now you can bet if you use a thicker oxide, you will find it's also different mobility because mobility also would be different. And it's more subtle than this, but if you do change the doping concentration, you will find mobility is also different. Okay? And if you apply a body bias and still perform this experiment with a body bias, you'll find mobility yet to be different. Is that right? All right. So this is a problem. Now, before we explain how to understand and simplify this complex problem, understand this complex situation, let me say a few words about this measurements, a bit more about the measurement, all right? When you make the measurement, you will find, say, mobility does decrease with increasing VG. I already mentioned that. As mobility increases, as VG increases, mobility decreases. But you also will see when VG is low, mobility also decreases. And for a while in the literature, it was not quite clear this is a real or this is just an artifact of measurement. It could be an artifact of measurement because this equation is known to be not accurate when VG is very close to VT. Why? We ignore the subthreshold current. Is that right? Right? We assume the current will be linear function of VG. We didn't consider this tail in the ID versus VG plot. Is that right? Is that right? Okay. And another way of saying it is we actually don't know what Q inversion is when VG is very close to VT. When VG is very close to VT, Q inversion is not equal to this. Q inversion is more complex. Remember the chart sheet model? This is only good for strong inversion. Is that right? So when we get to this low VG region, we're not quite sure this is right, number one. Okay? And but we do know now that it is correct. One reason we know that is we have a better way of measuring this mobility. We don't have to rely on this uncertain expression for the Q representation for the Q inversion, right? So let's say what we really want is we want ID equal to W mu VD over L times Q inversion. The Cox VG minus VT really should be replaced by inversion. Cox times VG minus VT is only approximation for Q inversion, right? It's pretty good approximation, strong inversion, but certainly falls apart when VG is close to VT, right? So the question is, can we measure Q inversion rather than relying on Cox and VT and VG? Can we directly measure Q inversion at every VG? We can measure ID at every VG. If we could also measure Q inversion at every VG, then we get mobility. All right? And the answer is we can. And this goes back to the first few weeks of this course. We talked about capacitance. Capacitance is equal to dqi dVg. Actually, it's dq dVg. Right? We can limit ourselves to only look at the inversion charge if we measure only one component of current called CGSD, CGS/D. S/D meaning source and drain are shorted together. Source drain are shorted together, as shown here. You see, source drain are shorted together. Is that right? Is it okay? All right? So together is one terminal, one node. Source drain is only one node. All right? We measure the capacitance between that node and gate. Between gate and that node. Gee, what are we getting? I tell you, the simple way to think about it is that you measure this, start with the strong inversion case. In the strong inversion case, source and drain and channel are all together. Is that right? So the capacitance we get is really just the gate to the channel capacitance. You following? Is that right? Okay. So for example, what you will find is that this is this curve, this whole curve, this portion. I'm just highlighting this portion for you. This portion is what we expect for CGS/D. Okay, let's see why. In the strong inversion, what's the capacitance we get? The capacitance we get, of course, is the channel capacitance. Is that right? Yes? Right? And that will show up as between CG and SD, because the charge in this inversion layer actually is supplied by source and drain. In fact, that's the only reason that we will see the so-called low-frequency CV, even though we may be using 10 megahertz for this measurement, right? Because the source drain are supplying the charge. So this current we see is the result of charge coming from the source and drain. Do you follow this? That's what we call the CGS/D. All right? Same thing. Any capacitance due to the inversion layer charge will show up as CGSD. All right? Now, will the depletion capacitance show up as CGSD? Let's see, in the depletion region, will the charge on this capacitor come from the source and drain? It would not. It comes from the body terminal, right? With charging, discharging, expanding, and contracting the depletion layer. And that charge comes to and from the body. Does not come from source drain. So in this portion, you will see nothing of the CGSD. That's why CGSD already will be 0 here. You follow what I'm saying? All right, question?
Isn't there also an overlap capacitance contributing to CGSD?
Let's handle that first. But first, maybe I'll handle that next. Let's first ignore the source drain overlap capacitance for now, all right? For now. Let's suppose there's no overlap capacitance. Now, do you see there might be a little tail here? You see, we're not making assumptions. We're not saying this capacitance will suddenly drop. In fact, this whole curve is measured. Remember, we're measuring the CV curve now, measuring between gate and source and drain. Now, I'm telling you, if you measure this, it's not going to suddenly drop to 0, but actually gradually go from what you expected to come from source and drain until some point it becomes 0. And eventually, you don't see anything because all the capacitance between gate and substrate, which is what you expect. Can you try to explain where this tail comes from? What is this tail about? Why doesn't this curve suddenly drop to 0? It's probably to 0 like that at Vg equal to Vt, perhaps. Yes? Please.
Is it because the inversion charge doesn't disappear abruptly?
Absolutely. Thank you very much. Now, the fact that the inversion layer charge doesn't suddenly drop abruptly to 0 is at least part of the problem we're trying to solve, of course, because that assumption using Cox times Vg minus Vt did not consider that, right? I said part of the problem, not the whole problem. Why it's not a whole problem? Not only this equation assumes charge suddenly go to 0 at Vg equal to Vt, it also assumes the capacitance immediately goes to Cox at Vg larger than Vt. That's what this equation is about, if you think about it. All right? All right. So in reality, we don't make the assumption. We just know we can measure this capacitance, and this capacitance is equal to dqi dVg. Therefore, if we integrate this capacitance with respect to Vg, multiply dVg to the left-hand side, integrate it, we will get Qi as function of Vg at every Vg. Do you follow? Is that right? Okay, good. Now back to the question about overlap capacitance. If there's overlap capacitance, what will be the change? The change will be this will not go to 0, but rather will saturate at some point that's not sensitive to Vg anymore. Is that right? Because the overlap capacitance is constant, at least to the first order. It's independent of Vg. Is that right? Yes? Are you following what I'm saying? Right? So this whole original curve will just be pushed up by a certain constant overlap capacitance. Put another way, it will look something like that. But this is fine. This is, in fact, is excellent. Why is excellent? It gives us automatically a 0 point. You see? Not only we can take care of the overlap capacitance, in fact, we don't even care whether this is the overlap capacitance between the source and drain or because the probe capacitance or some straight capacitance. But anything that's independent of Vg, we know could not be part of our dqi dVg. Is that right? Is that right? All right. So to give this automatically give us a reference where you cut off. You see? If you didn't have this effect, you are actually in trouble because very often we have to, for example, this often is a big trouble, is this one. How do we know this is the real minimum capacitance corresponding to the depletion region thickness? How do we know there's not a probe straight capacitance? What we sometimes do, we just lift the probe so that it doesn't touch the contact. But does that mean all the capacitance goes away? Doesn't the probe still have some capacitance left? Right. So this actually is a very, very good plot, this technique. It's very, very good. All right. In fact, it's a better way to determine oxide thickness than using these, because using these, I already mentioned to you, there are problems like the probe pad capacitance, for example, right? And you lift the probe, maybe probe pad capacitance away, but what about probe capacitance itself, right? Okay? So with this, you don't have to do anything. You just keep the probe down, but you still have a reference to know where it's 0. Following what I'm saying? All right. So this is how we can get Qi as function at every Vg. And we just substitute that into here. And also measure ID at every Vg. We'll get mobility at every Vg. Is that right? It's okay? All right. Questions? Okay. So if you do that, let's say we have a very good knowledge of the experimental data of mobility now. All right? So it generally looks like this, in this shape. And interpretation, there's no dispute about what goes on here. This is the part that's least dispute, is that it's due to Coulombic scattering. Coulombic scattering can have come from several sources. One is ionized impurity, just because substrate has a doping concentration, therefore there's a dopant scattering, right? Right? So one advantage, additional advantage that I have not mentioned to you that people would like to take out of the retrograde doping is that there's a less doping smaller dopant density near the surface where the electrons and holes move, and therefore there's less Coulombic scattering. Is that right? All right. There are any other charge near the surface could also cause scattering. Interface charge scattering, trapped interface traps, and we already talked about this when we talk about the telegraphic noise of MOS transistor or 1/F noise. Remember? Yes. Okay. So that comes from the Coulombic scattering. If you read a paper about a 1/F noise, you will notice it's very important to remember there is something called screening, which will make the severity of Coulombic scattering go low, go away when Vg is large. Because when Vg is large, there will be a lot of inversion charge near the surface that will screen away the Coulombic scattering. As a result, the mobility will increase. So the mobility due to the Coulombic scattering alone is this curve. All right? You follow what I'm saying? Okay? Roughly speaking, it's almost linearly proportional to the inversion charge, Qi. All right? So depending on whether we're plotting log or linear scale, don't know how to plot this curve, but this component, due to the Coulombic scattering, this mechanism goes away fairly quickly as you increase Vg. Yes? Okay? All right. So therefore, the Coulombic scattering, specifically the benefit of, let's say, the retrograde doping in this respect, goes away when Vg is large. When Vg is, close to Vt, or when Q inversion is small, it's important. When Q inversion is large, it becomes relatively small, that benefit. All right? So what is responsible for the mobility here? There are two phenomena. One is phonon scattering. All right? Maybe I'll add that word, phonon scattering. Okay? One is phonon scattering. And the question then you would ask, why would phonon scattering be dependent on the vertical field? Why would phonon scattering decrease as the vertical field increase? Well, the explanation is not so clear. There have been several explanations. They all seem to be pretty good. In fact, there seems to be more reasons for there to be dependence on Vg than we really need to explain the experimental data. It can increase for the following reason. It's because, turns out, as a result of quantization, as a result of pushing the electrons to a higher energy, the density of states increased compared to without quantization, compared to without a strong vertical field, say in the bulk. And when density of states increases, mobility decreases. This is because mobility is related to scattering rate, and scattering rate is proportional at least to the density of states. If there are more density of states to scatter into, there will be higher scattering rate. Okay? Other reasons proposed, for example, a student, Igor Polishek, just recently submitted a paper, his student at Berkeley. He thinks what may be happening is simply just because as the result of this high vertical field, there's a tail of the wave function that penetrates into the gate dielectric. And gate dielectric typically has much lower mobility than the electrons in this crystalline silicon, as you can understand. All right? And just because of that, he can show that it's enough to explain what we have. We observe, as we're saying, we probably have too many explanations to explain what we actually see. So the problem is now we don't have enough explanations. We'll probably have too many to understand why the phonon scattering can still decrease with increasing Vg. Yes, question?
Max occurs at roughly what kind of VD set, or what bias condition do we actually get maximum?
It's hard to answer that. I would say this probably peaks around, let's say, what's the best way to answer this? All right, VT is certainly here. Let's say VDD is here, let's suppose, all right? And typically, it's probably, 1/3 between VT and VDD, so somewhere here, perhaps. Okay? So phonon scattering can certainly also decrease with increasing mobility, both experimentally and mainly some theory, including what I just mentioned about this wave function tailing into the gate dielectric, actually predict it proportional to EOX to the minus 1/3 power. And sure enough, if you look in this plot, somewhere you fit e to the minus 1/3 reasonably well. But I don't want to overemphasize that. It doesn't fit over wide range, all right? Okay. Specifically, the slope seems to go, if we were looking at a log-log plot like here, let's say, you always find a region seems to fit 1/3 okay. But later on you will find it actually goes beyond 1/3. Goes to 2/3, 3/3, in fact, go beyond 1 even. Now that's a little scary, isn't it? Going beyond 1 means what? Meaning if we double the VG, roughly speaking, I'm not being exact here, you can reduce the mobility by a factor of 2, right? By more than a factor of 2 if it goes beyond the slope of -1, right? So let's say -2. That means you double the VG, your mobility would decrease more than a factor of 2. Yes? And yet your QI would increase by how much? At most by a factor of 2, right? It's proportional to VG minus VT. So you lose your mobility by more than a factor 2. Even though you increase the charge by factor 2, what can you expect for your ID set? You're supposed to see less current with increasing VG, right? So when you really look at this curve, all kind of questions came out to be. Well, it turns out part of the reason is because the topic of the next section that saves the day. That is, because of velocity saturation, current is not truly proportional mobility, fortunately. If it was, we would have bigger problems than we are in, all right? But fortunately, the current is not proportional mobility. Of course, current is affected by mobility quite significantly, but it's not strictly proportional too, all right? So I'm just emphasizing how important it is, this dependence between VG and vertical field. So in a certain region has been shown both theoretically, well, probably more theoretically, experimentally, it has a relationship with E oxygen minus 1/3 if it's a phonon scattering. And certainly, phonon scattering also, okay. So then we still need something to explain what goes on beyond that. You know, this additional loss of the mobility beyond what this surface mobility scattering can show us. Well, most people agree it has to do with surface roughness scattering. All right? You know, in a way, this is an easy scapegoat because we don't really have a good way to measure the surface roughness, first of all. And secondly, there's also some uncertainty about, even if you know the surface roughness, what is the mobility, right? If you really look at the theory, there's some unclear things. For example, the surface roughness supposedly to give you a temperature coefficient such that mobility should increase with increasing temperature. Right? In other words, you should have similar behavior as Coulombic scattering in temperature dependence. But in reality, we know it's not. The mobility decreases with increasing temperature, even as phonon scattering would predict. Another difficulty of thinking that this is the final answer, surface roughness, although, you know, given that we don't know how rough the surface is, of course, you know, you can, it's an easy way out of this problem, just say surface roughness, is that what's interesting is that every lab is getting the same mobility. Not only that, every lab has been getting the same mobility for the last 20 years. Is it by chance everyone have exactly the same surface roughness? And all this work has improved the surface roughness? So that certainly is a good food for thought. So I consider it still an open question. But I can tell you, if you ask engineers, 95% will say surface roughness. And that's certainly fine. To the extent we cannot prove it's not. Actually, one student here did try to prove it's not. He used what's known in the literature to make the surface rough, that is prolonged rinsing in DI water. And he rinsed his wafer in DI water for more than 24 hours. And he found out the mobility is the same compared to a control sample. So, you know, that certainly casts a little more doubt on this roughness explanation. So there's still some questions about what it is. But it's very important to remember that if we're talking about a good SOI, SiO2 and silicon interface, all right? Everyone's getting some mobility today, okay? Now, there are very, let's say, rare exceptions to that, and it's believed that the most likely way to create a non-standard mobility versus vertical field behavior is nitridation. So let me not get into that. So it's generally agreed that nitridation will change this curve. But other than that, if it's SiO2 silicon interface, the fact is that everyone has been getting the same mobility and still getting the same mobility right now. Right? That's a very important fact because that really made the modeling possible. If not, you cannot predict what behavior transistor will be until you make it and figure out what mobility is. Is that right? Fortunately, we don't have to. Mobility is very predictable, turns out. All right? That's not responsible for any our lack of knowledge of the transistor behavior. It's not mobility today. Yes?
When we say the mobility, is it the bulk mobility of the silicon?
No. Any mobility we say in this section, this chapter, maybe in this course, is the surface mobility. Only the inversion layers, only mobility we're interested in.
And also, in previous lectures, we said that the inversion layer is like slightly under the surface, right? So it doesn't go through the surface. I mean,
doesn't matter. So in that case, you have to you interpret the surface a little bit loosely. Wherever the current is flowing, we're measuring the mobility. That's why I start by telling you how we measure mobility. It's measured by measuring ID. So whatever determines that ID is the mobility we're talking about. But a standard term is that we do say this is surface mobility. Sometimes say, actually, a very common term is effective mobility. I was waiting a little later to introduce that to you because I don't think it's very descriptive. Nothing effective about it. It's mobility. It's true mobility. You cannot define mobility any better than this. It's you come from the current and you know the field, which therefore is the mobility. It's nothing effective about it, right? So it's really the mobility. But you're right. It's not necessarily meaning right at the surface, but whatever that inversion layer charge flows is the mobility. Okay? Okay? And there you can already see why there's so many explanations for this VG dependence, because where the current flow also varies with VG, right? So plenty of reasons. And so let me just think by saying, I wouldn't be surprised more and more we'll be able to explain these by phonon scattering as well. As we're saying, right now we have more than necessary to explain what is this field dependence by the phonon scattering, right? Okay. But nonetheless, I think 95%, if not 99% of engineers will say this is surface roughness, and I certainly also agree that there can be surface roughness contribution. The question is, in reality, when you're given a state-of-art sample, how much is due to surface roughness? I think it's very, very uncertain at this point. All right? Okay. By the way, another possibility is that, and maybe someone can argue why there is, all the sample have really the surface roughness because it's determined by some thermodynamics. At a given annealing temperature, there was always going to be that roughness. That's also possible, since everyone uses about the same temperature, therefore that's roughness. So those are interesting questions, right? All right, let's see. Okay, good. Any questions about these three mechanisms of scattering that's generally accepted? There's the phonon scattering. There's the, I think it's very important, but most engineers actually think this is a surface roughness scattering. And finally, in the low VG region, there's the Coulombic scattering. Everyone agree that's what's responsible for the mobility fall. Okay, any question? Okay, and the carrier scattering and the mobility scattering, mobility falls with falling VG is expected behavior of screening. All right, when we don't have mobile carriers screen these Coulombic centers, then mobility will be very low. Okay? All right. A breakthrough in the modeling of the mobility came, and this is phenomenological model that is not answering the question of what is responsible, what mechanism is responsible for mobility, all right? Not answering that. But what's found that although mobility is function of VG, function of Tox, function of N sub, function of V sub, turns out Clemens and Sabonis of AT&T Bell Lab found out they can unify all this dependence with one function, that is mobility is function of something called effective vertical field, E effective. And the effective vertical field, furthermore, is defined this way. Let's look at this. E effective is defined as the depletion charge plus inversion charge, half of the inversion charge divided by epsilon. All right? Whether it's epsilon s or epsilon ox is not important, just a factor of 3 difference, although it's defined with epsilon s in the literature. So what's the meaning of Q depletion and plus Q inversion over 2? There's a very simple interpretation right now. Well, maybe I'll give to you right now. The interpretation is it's the average of the electric field underneath an inversion layer and on top of the inversion layer. Let's first look at underneath the inversion layer. Suppose I draw a Gauss box, right? That includes, all the depletion region. The electric field on the bottom is 0, right? If I draw the box dp now. The electric field here, which is the electric field under the inversion layer, would therefore be what? Be Q depletion divided by epsilon s. Do you agree? Yes? Now, what's the electric field on top of the inversion layer? Of course, we just move the top boundary of Gauss box a little bit more to enclose the inversion layer itself, right? So that would be the charge in the new Gauss box, which is Q depletion plus what? Plus Q inversion divided by epsilon s. Do you agree? Yes? And if you add the two together, take the average, what do you get? You get Q depletion plus 1/2 of Q inversion over epsilon s. Do you agree? All right? So in hindsight, kind of makes sense. Probably, they're kind of makes some sense, although it's really, no more explanation than that. It's just that it's an empirical observation, right? Empirically, just found that if you calculate this, calculate that, add the two together, divided by epsilon, and plot mobility versus that, turns out doesn't matter what Vg you use, doesn't matter what Tox you use, doesn't matter what doping concentration you use, doesn't matter what V sub you use, you get one simple curve. That's nice. Not only is one simple curve, but in fact this curve is the same whether it's made in Hitachi or made in Samsung or it's material made at Intel, right? And that's really nice. That's why it's called universal mobility. Correct? Do you follow what we're saying? Okay. That really made the mobility description easy. Okay? All right. Yes?
Is this Q inversion calculated from Cox times Vg minus Vt?
Well, we can talk about that later. Yes, usually people would measure that way, all right? And that's probably pretty good enough. Yeah, Cox times Vg minus Vt is inversion, Q inversion, yes. Okay? All right. And so this field then is given a name called effective vertical field. Well, this word effective, of course, makes sense because it's not effective field at any particularly known point. It's kind of the average field in the inversion layer. You see that? It's the bottom and the top, kind of average. So it's called an effective vertical field. Okay? Yes? And this also highlighted this concept that mobility is function of the vertical field. That certainly makes sense, right? And specifically, this is a definition of effective vertical field. All right? So far, we still kind of say that qualitatively there's such a dependence. But in fact, we can even quantitatively try to fit this measured data to a universal function. And the function, many people have tried to do that, and they all come up to some functional form, something like that. A constant divided by 1 plus E effective over some constant to a constant power. Question?
Okay, I think that's what you just said, but linearly connecting the points between the two fields, as in literally taking the average, is that unoperative? I was just asking the benefits to try to fit something different than linearly, assuming that the field just linearly slopes from the Q depletion to Q depletion.
What do you mean by linearly slopes from? Maybe I misunderstood your. Which function are you pointing at? I point at the one I'm pointing on now, or this one?
Yeah.
Ah, very good. In other words, you say maybe this should not be 2, should be 3, or this should be square.
Right.
Yeah, that's right. as far as I know, no one has reported the complex fit like that, but I have to assume that Clemens and Sebnes, when they did this, they probably tried a few other things. One thing is that people have reported, this is widely accepted, that for whole mobility, this should not be 2, but rather 3. Okay? That again gives us a hint. There's nothing so kind of magic about this effective field, or just saying some kind of average between the top and bottom field, right? How you take average is still uncertainty. We don't know exactly what to do, all right? Okay, so 3 for whole mobility for mu p, all right? This is often used in the literature, okay? Good, other questions? All right, back to this functional form. So many times people would give empirical fit. And this is a set of fit that we have found to work quite well. So, here it is. And there may even be a reading for this, certainly interesting reading on this. That's right. There is one reference to read, if I can just remind you from in the previous slide. This reference is given in your in the handout, and this is from Dr. Takaki of Toshiba Corporation. It gave a very detailed experimental study of the mobility data and some interpretation in terms of mechanisms, and so it's a good reference. All right. All right. So this is then empirical fit to experimental data. Any questions? And these values are given here. So if we knew this effective, we know the mobility. That's quite a strong statement. Right? Yes? Question?
Mu naught would be the mobility in the absence of an electric field, right?
Mobility mapping?
No. Mu naught would be the mobility when there is no electric field.
I don't want to overemphasize that physical interpretation. This is not a physics model. This is curve fitting. We know it fits this portion right. We don't know whether we can extrapolate all the way to E equal to 0. All right. When you go to E equal to 0, does this become the bulk mobility? Obviously, it's not. You can see it's not. All right. It's just curve fitting. Okay. But it's a universal curve, and that's very powerful. Doesn't matter on the detail of these things. It only depends on one thing, this average vertical field, and also everyone is getting the same mobility. Now, this, of course, good news and bad news. The good news is that you don't have to sweat too hard. You know, other people are not making better mobility than you are. The bad news is you cannot make it better either, right? than this either. But I did say that there are exceptions. Exception is the strong nitridation. When the surface is not SiO2, then its known mobility would be different. Okay, and certainly opens a lot of questions about the future different dielectric, high K dielectrics. What if it's not SiO2? What can we expect? What's in store for us? And you cannot answer those questions until you have some reasonable understanding about SiO2 system. Okay. All right. Good. So we have already said this in the previous slide. The interpretation of this really is the electric field on the bottom of the immersion layer is Q depletion over epsilon, and electric field at the top of the depletion layer is Q depletion over Q inversion over epsilon. And if you take the average, you get this E effective thickness. All right? But we don't take this too seriously because for whole mobility, 1/3 is better. So what does that mean? All right? Okay. Another thing is, by the way, maybe I'll ask you, I'll suggest to Kevin, maybe give you essay homework. We can try that just for fun. It's really a mathematics problem, and maybe you can say electrostatics problem rather than physics problem. Turns out it can be shown that this definition, all right, or this one, let's just say, is really equal to electric field. Let's say at any of this, let's call this, what direction did we call this? We'll call this x direction, I believe, right? Right? At any x, right? Times the charge density of that x, dx, and then divided by rho x dx. What is this telling us? It's an average electric field weighted by the density of rho, right? Is that right? Yes? Okay. turns out you can show it doesn't matter what waveform this, what functional form this rho has. In other words, including even quantum mechanical wave function. All right? You can show that this has this interpretation. It's a very clear average. You see what I'm saying? It's average electric field weighted by the density of the immersion charge. You following what I'm saying? Okay, that's pretty powerful. Okay, of course that then backs to answer the question. Then how do you explain this 1/3? Well, then we're back to we don't really know what it is. All right, but it's some kind of average. But this, at least, it's a mathematical of some mathematical interest that you can show this is equal to that, no matter what rho is. All right? Okay. Hey, Kevin, maybe you can consider assigning that as a homework. I'll give you one solution to that. All right. Okay. Okay. So that is a very useful model to relate all the mobility to this one quantity called E effective. The only problem with that is that E effective, although if you want to sit down and try to calculate it, it's not that difficult, but in reality, in practice, it's rather elusive. I'll give you some examples. You know, if you ask, let's say, Daewon, he probably developed some technology from Samsung, and let's say, suppose he developed the 0.18 micron technology, and you ask him, what's oxide thickness, what's VT, what's maybe even the doping concentration, or even profile, he'll be able to answer all that questions. But you ask him, what is E effective at VG equal to VDD? I bet you he's going to draw a 0. He'll have to go back to his computer, try to do some simulation, and find out what it is. Another problem is that, you know, this concept of E effect of the Q depletion is very complicated, especially looking at shorter channel device other than the very long channel device, right? What is the charge in the depletion region? What is XD max, right? Think about a cross section. Where is the boundary of depletion, right? So these are, turns out, it's a very useful model, except that E effective is not something that's easy to calculate, and certainly not something that we can come up with easily for given technology. So I'm going to give you another step forward in making this model even simpler and closer to what we work with. That is, we can rewrite this Q depletion, Q inversion, or rewrite E effect, not in terms of Q depletion, Q inversion, but only in terms of VT, VG, and TOX. Now, if we can do that, that's pretty good, don't you think? Right? If just by giving you VG, VT, and TOX, you know E effective, then there will be no problem to answer what is effective, not only at VDD or any VG. Right? Is that right? So if you know VT, and you know VG, and you know TOX, you know E effective. Right? How can we do that? We'll do it this way. First, look at the Q inversion term. Q inversion certainly can be related to the COX or TOX and VG and VT. That part is trivial. Is that right? Is that right? The question is Q depletion. Do you know how to relate Q depletion to things like VT and VG and TOX? I'm blocking one function. I want you to just think for a moment. How to relate Q depletion to VT, VG, TOX? How about this equation? You see, we don't really have that many things to remember, right? So I haven't drawn many boxes around the equation that I want you to remember, right? But this is one I think we should all remember. We certainly have used many times. We're going to use it yet again in a very different way. VT is equal to VFB plus 2 phi B plus Q depletion over COX. So here's our chance to get a Q depletion in terms of COX and VT. Yeah? Provided we know VFB plus 2 phi B. Do we know something about VFB plus 2 phi B? Could you speak into the microphone, please?
Well, it's about minus 0.1 or 0.
Thank you, thank you, thank you. VFB plus 2IB is about 0.1 or 0. Today, for simplicity, I'm very glad you remember it's actually not 0, but 0.1, all right, or minus 0.1. For M plus M MOSFET or P plus P MOSFET, both happen to be 0. So therefore, VT is equal to Q depletion over Cox. Therefore, Q depletion is equal to Cox times VT. Well, it turns out Q depletion term is even easier to deal with the Q inversion. Okay? Yes? All right? Yeah? Okay. And if you now add this together, Q effective is equal to Q depletion, which is Cox times VT. This term is the Q depletion term. Yeah? And 1/2 of the Q inversion is this, right? This is 1/2 of Q inversion. You see that? Yes? Divided by epsilon. Then what do you get? You collect the common terms. They all have Cox. You take it outside. Inside the parentheses, what do you get? VG, what? 1/2 of VG plus 1/2 of VT. Is that right? So VG plus VT over 2. You see that? Yes? It's okay? And I'm almost finished, but if you want to continue, it will be what is Cox equal to? Cox is equal to epsilon ox over Tox. Is that right? And this gives us 6. 3 from the ratio of the epsilons. 2 is the 2. We'll get a 6. Okay? So now we know E effective very simply. If you tell us VG, VT, and Tox, we'll get E epsilon. And once we know E epsilon, we know the mobility. Okay? So this is called universal mobility model. All right? I'll give you some interesting applications of this. You know, we said the mobility is function of VG. Certainly it's function VG, you see here. We said mobility is function of Tox, right? You see it here, no problem. We also said mobility is function of N sub. Do you see where that might come in? It's VT, exactly, because it's the Q depletion term. We said also a function of V sub. Do you see where that might come in? It's VT again. Remember the body effect? The reason the mobility function of V sub is because when you apply V sub, there's more Q depletion. And therefore, there's less mobility. And that's automatically captured by VT. Right? So it turns out VT plays a very important role. Okay? I'll give you another example of how to why it's so important to know these facts. You see, this is probably the only time you have seen VG plus VT. Everywhere we see is VG minus VT. Is that right? Okay. So therefore, it will not surprise if you tell you that very often when engineers try to optimize this device, right? He designed the device slightly differently, yes? Okay, maybe the implant, the dose change, and so on and so forth. And you want to see whether it has changed its mobility. Okay? All right? Yes? But because these are two different devices, different implant maybe, so VT is always slightly different. And yet he's trying to compare the mobility. Right? For example, maybe he did a retrograde well. He's saying mobility is better. He's trying to see whether the mobility is better or not. But these two devices have slightly different VT. Guess what this engineer is likely to do when he presents the data? If you were an engineer, how would you present this data? Vertical axis mobility. What would you plot in the horizontal axis? If you simply do VG, is that fair? Usually not fair. So how would you do it? Okay, you will find many times engineers will plot VG minus VT, right? And they will find one is a little higher than the other. Do you know what they're going to conclude? They say this technology has better mobility. And you better believe this usually is the one that he's proposing as his new idea. This is the control. All right. Now, in reality, of course, it's a very different result if you plot this against VG minus plus VT, which is the proper way of doing it. Do you know what I mean? Okay. If the VT has differed by 0.2 volt, whether you use plus minus VT or minus VT, you will shift one of the curve by 0.4 volt. You can easily reverse the conclusion. That's, again, reason why we want to know what is the theory behind certain things before you plot it, right? It's not just to say, because we see VG minus VT a lot, therefore, in mobility comparison, also plot VG minus VT. It should be VG plus VT. Okay? And not only is the better way, in fact, has very strong link and very solid ground all the way to the common universal mobility, the concept effective field. Okay? All right. Another application, maybe it's a word of caution, is that what if we don't have M plus poly on NMOS or P plus poly on PMOS? Maybe because you're dealing with a metal electrode later on in the in your study, or maybe because you're dealing with some, well, okay, it doesn't matter. Today, let me give you an example. Maybe because you're dealing with M plus poly on P MOSFET. Okay? All right? That's a legitimate example, M plus poly on P MOSFET. How do you think this should be changed? What's in the top half of the paper should be changed if we're dealing with M plus poly on P MOSFET? Which of the steps should be changed here? Is this still correct? No, right? Instead, VFB plus 25B will be equal to what? About 1.1 volt, right? Because the VFB changes by the band gap. Nothing else has changed except VFB changed by band gap. Is that right? Yes? Yeah? So therefore, you can show that there should be a plus 1.1 volt here somewhere. Okay? I'm sorry. It's not this. 1.1 volt should be here, something like that, right? Yes? So this should be VT. I don't remember what's plus or minus. Maybe it's minus 1.1 volt here. Okay? Yeah? And when you put it in here, minus 1.1. What would you get here? We'll get minus 2.2, isn't it? Is that right? Yeah? And indeed, when the student went to check this, guess what he found? He found that if he took the M plus poly and P plus poly and plot them against this, he found exactly shifted 2.3 volt. Okay? That makes a lot of sense, all right? Now here, however, leads to another interesting discussion. That is, if you did not know this model, because I told you, start with this known model that seems to be trivial, right? But I tell you, for decades, I think there's a question. I believe it's a wrong understanding about how to understand this curve here. You see, this is known, by the way, you have heard this term. I think I briefly introduced the term surface channel and buried channel when I introduced P plus poly PMOS and M plus poly MMOS. Did I use that? Did I not? I didn't? I'm sorry, maybe not. Okay, let me tell you. P plus P poly is known as surface channel PMOSFET, PFET. Okay? Now, if you use M plus poly as the gate material for PMOS, what you will find is the VT normally, if you don't dope this heavily, normally will be very high. It's minus, say, let me call this 2 volt or something. Okay, depending on oxide thickness. I'm exaggerating this a little bit. All right? So in order to bring the VT down to what you want, the standard practice is you implant boron into the substrate. I think I did mention that. All right? Right? Because you implant boron, it's as if you have boron here, right? It's p-type, right? Yes? Therefore, people call this buried channel device because current is not flowing to the surface, but rather flowing to the bulk. Are you following what I'm saying? I want to tell you, I believe this is a misnomer, but this is the standard terminology for decades. And I believe there's this misnomer, there's this misconcept that M plus poly current flows in a subsurface in the bulk, partly because of this data. It's well known that if you design 2 transistors, one with P plus poly, one with M plus poly, you manage to get the same VT, right? Of course, one requires implanting boron, one implant the phosphorus maybe. And you measure them at the same VG, and they have the same oxide thickness, which really means identical condition. You see what I mean? Same VT, same VG, same oxide. It's well known, has always been known from early on, that N plus poly design give you higher mobility. Now, why should the mobility of this transistor be higher than the usual design of transistors where current flows at surface? Hey, doesn't it make sense? It's because here the current is flowing not at surface, therefore no surface scattering, but because it's flowing in the bulk, therefore have a bulk mobility. So this data actually fuel the concept that this design is a buried channel transistor. Now, for those of you that have been working with companies, you know it's a standard terminology, buried channel transistor. But I bet you if you do a 2D simulation under at least strong inversion, see where the current flows. Certainly this is strong inversion. That's where the mobility is measured. Guess where the current is flowing? Definitely it's at the surface, all right? And it actually will be very interesting for you to try to draw some energy diagrams, see if you can prove to yourself. It has to be at the surface with the kind of voltage we're talking about. Yes?
But the flicker noise of buried channel devices is consistently measured to be lower than surface channel devices. So
I would like you to also try to explain that as maybe if a question we can discuss that in the discussion hour later. But hear me as I finish this mobility. All right? Okay. So, all right. So we know the electron is flowing at the surface, not in the bulk. Yes.
But that question was related. I mean, if you get lower, would that not be an indication that it's not flowing on the surface?
No. I don't believe so. All right. So what's the possibility that what's the explanation therefore? And in fact, that could have something to do with help answer that question as well. Is it possible that both devices with the carriers flowing at a surface and yet the mobility are different? Is it possible? If you can answer that question, then you can say you've understood the topic that we covered today. That is why even for N-channel transistor, the mobility is function vertical field. So let's go back to the N-channel transistor. Before I started this topic, you have no problem understanding the curve should look like that. Is that right? Certainly at every of this point of different VG, we're talking about surface channel, right? Is there any question we're talking about surface channels throughout? Yet, just because vertical field is higher, mobility can be different. So why can these two transistors not have two different mobility even though both are surface? All this telling us is that they have different vertical field at the same VG. Why do they have different vertical fields here? It's just that, right? So if you cannot answer that, maybe you should think again. Why is mobility a function vertical field? I try to give you some answer with the phonon scattering as example by saying if the vertical field is strong, perhaps there's a wave function tailing into the gate oxide, you can have more scattering. Yes? Or maybe because the ground state energy is higher, you end up with higher density of states, you have more scattering. Is that right? Yes? And certainly if it's due to the surface roughness, then the argument is that the stronger the surface field, then, quote unquote, the closer the oxide, the charge is to the surface. Therefore, there's more surface scattering. Okay? This last picture is a very interesting picture. I actually like that picture, but I can tell you I've never seen one to try to analyze that theoretically. In other words, if we knew the surface location of the charge, conduction charge is function of Vg. This is from the quantum mechanics analysis. We know the charge thickness. We know the centroid, right? From that, can you somehow figure out why the surface roughness should give us a mobility versus Vg in this manner? If you can derive that, then certainly would be very good to use that to confirm the explanation of the measured data as being due to that mechanism to see if it agrees. But I can tell you the only well-known model for the surface roughness scattering, the only one I know and believe the only one well-known, is actually very interesting. It models this way. It says, okay, roughness in model this way. Because we have a rough thickness, therefore the oxide thickness is varying. You see what I'm saying? Because if oxide thickness is varying, then electric field is different. Here, here, here is different. Let's say at a valley and a peak of this surface roughness, the vertical field is different. Yes? If the field is different, phi s is different at the peak and the valley. Surface potential is different. Do you follow what I'm saying? Yes? If phi s is different, we're having a periodic variation of the potential, and that scatters carriers. So in a way, today's surface roughness scattering model is actually quite probably different from what you would have thought. Certainly it's different from what I would have thought. But that is what is the surface roughness scattering theory in the literature today. All right? And so if you look at that theory, it has very, very little dependence on the separation between these surface and the charge location. The reason is that charge location does not change that much in this range once we're in the strong inversion. Does not change that much. You know what I mean? And secondly, it's because Coulombic scattering. You see, this basically went back to the Coulombic scattering. It's a variation in the potential, so it's a Coulombic scattering. And Coulombic scattering is fairly long-term interaction. I mean, long-range interaction. So a few angstrom change in the location of the charge is not going to change that too much. All right. So whether it's a surface or not surface is not important to this. Okay. Any other questions about the mobility theory? Okay. All right. So it's probably more than what you expected, but this is very important. Because if we don't know the mobility, then there's no way to really know about the current, right? Okay. So here I show you some data to verify the universality of this mobility model. The solid line is this equation that we've shown you a few slides earlier. I was saying there's no fitting parameter anymore, right? You know, what were power, what mu naught, you were asking, is mu naught a zero field mobility? Those were all determined, right? But once you determine that, so here it just shows you, you know, say each symbol is different doping concentration. So there are 3 groups of doping concentration. Is that right? Is that right? And for each group of them, actually, one would, in this particular case, would use 2 different bias voltage. Body bias. Is that right? And within each curve, of course, is changing Vg, you can expect. Is that right? So no matter what you change, you end up with one curve. That's the meaning of universal mobility. You see what I'm saying? Okay. What's happening here? What's causing this to drop? If we plot more, it will be even clearer. I believe this stopped at Vg equal to Vt. But what is here? What is thing here? How come this mobility doesn't agree with the so-called universal mobility so well at low Vg range? That's the Coulombic scattering. This happens when Vg is close to Vt. Is that right? So you can see, for example, this group, it starts here, deviate here. This is the group. I would not force you to read the symbol. Once you read it, you will see. It's the one with the 2 × 10⁸ of doping concentration. Therefore, Vg is very high. Is that right? Yes? So on the scale of Vg, Vt is very high, I'm sorry. So on the Vg plus Vt, it comes to be very high. Is that right? Okay. All right? Yes? Okay. And of course, this particular plot did not show you data of different oxide thickness, but there may be some reference that I gave to you, maybe I did not, where you put different oxide thickness, you will find they also come on the same curve if you do it this way. All right? And also on this, we showed there's a different curve describing the mobility for holes. In fact, holes shows even better plot. We see less of a Coulombic scattering. Okay? And in a way, the kind of may or may not have to do with what you said about the noise, but it's a fact. We actually see less of Coulombic scattering in the whole case usually. All right? Now, why is that the case? We're not too sure. There are several possibilities. Perhaps because we simply have less interface traps in the PMOS than NMOS. It's possible. Now, maybe because of the difference in the effective mass between electron and holes, the location of the holes and electrons is slightly different, or they respond slightly different to the Coulombic scattering versus the phonon scattering. And Coulombic scattering, we know, is responsible for the 1f noise. Remember, when we talk about the 1f noise is due to the Coulombic scattering. Remember that, right? That's mobility fluctuation. It's when the charge go into the interface trap, it becomes scattering center. Is that right? Is that right? Okay. We don't know why that's the case. Now back to the case of PMOS versus NMOS. What might be the difference of the noise? I don't know the answer to that. But just like I said, mobility can be a function of vertical field. In other words, even though both transistors are surface transistor, just because one does not push the electron as close to the surface, right, could give us better mobility. I can imagine that also could give us better noise. There's less coupling between the oxide and the interface traps. There's less overlap of the wave function, the penetration of wave function into the oxide. Do you see what I'm saying? Yes.
It seems like the buried channel device, for some reason I heard that that's going away, that for very, very fine line, it's just not engineered.
Yes, and we will talk about that in other lectures. Let's talk about that, all right? I want to ask you a question about this 1/n noise, buried versus surface channel. Maybe you can share experience with this. Is this something you have some personal experience with, or just something you heard?
No, for me, it's personal.
All right, great. So you had a choice of using so-called N plus poly and P plus poly device. Is that right?
Right.
All right. How much difference do you see in the 1/n noise?
It depends on the generation. 5, factor of 5, factor of 3.
Okay, that surprised me a little bit. It's that large. I thought maybe less than that. Certainly 2 would be very understandable, but 5 sounds surprisingly large. I can tell you that whether surface channel mobility or MOSFET, all right, or bulk so-called buried channel MOSFET, both are known to have order of magnitude larger 1f noise compared to something like so-called JFET. I don't know if you've ever had a chance with that. JFET, no one had any argument, not even from me, that it is a bulk device. All right. If you don't know what JFET is, no problem. Don't bother to look that up. But JFET truly is a bulk device. It has no surface. And when we look at that, it's order of magnitude difference in the noise, because it does not have the surface effect. So when we look at the P plus N plus, I was hoping the number is much smaller than 5. True, I can see that. So certainly, both are surface devices. It's not neither of this. Of course, I can also see if someone truly wants to design a buried channel device, he can, by the way. You just simply implant that channel with very heavy boron, such as VT is, minus, becomes the enhancement mode. I have no question about that, all right? If that's what you want, I can certainly see that can be done. But what I'm saying is that in a real so-called buried channel device with a right VT, right, that everyone calls buried channel device, it's not buried channel. If you look at where the current is flowing, both from simulation or just from your knowledge today, if I give you a homework, I believe you should be able to prove this yourself, that it is a surface channel device. Okay, in on state. All right, I didn't tell you about subthreshold region, so in subthreshold region we can talk about it again. All right, and that, by the way, also helps with this probably your experience. Your experience is probably biasing the transistor fairly low VG, probably, because analog application. And indeed, later I can show you at very low bias, the transistor will turn into a buried channel. In other words, in the off state, it's a buried channel. But when we talk about mobility, we're talking about on state. It's not buried channel, so we cannot explain the higher mobility just with the statement, it's a Barry channel device, right? To me, it's a little bit like, maybe not as, it may be, well, it's a bit like, just saying surface roughness explains everything. Right? So it sounds reasonable, but really doesn't, is not correct. At least it's the Barry channel part, all right? The surface roughness, I shouldn't badmouth that it may still play a significant role, but certainly it's not the only reason why we have low mobility here, right? Okay, other comments? That's very good discussion about the one-alpha noise. Thanks. So we'll take 10 minutes break, and when we come back, we can talk more about these or other matters.